So this formula right here is a very powerful formula that we can use. The dot product is a very simple calculation we can do, but what's really awesome is it relates to the angle theta in between the two vectors. So let's actually draw those vectors. I want to go ahead and prove this formula. Let's say we've got an angle U and another angle V, and we're going to connect them up like this. Now, what I want to do is I want to label this right here, and so I'm going to go ahead and draw these two vectors in a different way. I've got U again, and this time I'm going to go ahead and do negative V, and I'm placing them as if I'm going to add them together, which I am going to do. And so when you get the resultant addition of those two vectors, you get this guy, and it's U minus V, which is what we want right here. So we'll just go ahead and replace that vector I had previously drawn with actually U minus V. And then the angle theta is the angle in between those two vectors. That's the theta up here in the formula. I'm going to redraw that triangle and label the length, the magnitude, right? The magnitude of U, the magnitude of V, and the magnitude of U minus V. All right, so let's have a fresh page and look at this triangle. The law of cosines actually says this. The length of the side opposite the angle, right? If you square that, it equals one of the sides squared plus the other side squared minus this term here. That's the law of cosine, so we're just applying it to our beautiful triangle here. And let's get some formulas for the magnitudes of our vectors. So we know that the magnitude of U, given that this is the definition of U, is this lovely thing. And of course, if you square it, the square root goes away. Similarly, you can do the same thing for V. And U minus V, when you actually subtract the two vectors, you end up with that vector in component form. And just like before, it's a little uglier, but you have a formula for magnitude and a formula for when you square it. So let's go ahead and put those formulas in. Remember, we just talked about how this term can be replaced with this guy. And then this term can be replaced with this guy. And of course, the magnitude that's not squared is going to be a square root of that. And the same thing for the magnitude of V. So when we start our substitution, right, again, this is the same thing. So we're going to write that down. Let's substitute for this, put this in there. Same thing for the V squared. We know it's this. And lastly, this term is going to have those square roots in it. Pretty ugly, but it turns out when we simplify it algebraically, it's not quite as bad. Let's start by distributing this out, which just makes it bigger, but some of the things cancel. And it turns into a much smaller equation. Then notice that the negative 2's actually can cancel out, and you end up with this formula, which doesn't look very pretty, but this guy right here, that's the dot product. And this is the magnitude of U, and this is the magnitude of V. That's exactly what we've been trying to prove. So we have this formula, which is actually quite exciting. And we're done.